The management of refractive errors begins with a quantitative assessment of the refractive error. This is what we are going to talk about today. The suspicion of refractive error begins when there are symptoms of ocular strain or fatigue. There is headache related to ocular work after school or office work, or a headache which gets aggravated by ocular work. There is poor vision for near, distance, and both distance and near. Poor vision for near suggests hypermetropia or presbyopia. Poor vision for distance suggests myopia, and poor vision both for distance and near suggests high hypermetropia or presence of any other pathology, media haze, fundus, or visual pathway disease. A quick confirmation can be done by pinhole vision. Improvement with pinhole suggests presence of refractive error, and no improvement with pinhole does not exclude the presence of a refractive error. There may be no improvement with pinhole even though there is a refractive error in situations where there is a high refractive error, high astigmatism, central cataract, media haze, or macular pathology. We cannot proceed to manage a refractive error without a quantitative assessment. This can be done by retinoscopy or by a autorefractometer. The autorefractometer has made the process of assessing refractive error quantitatively quicker. Retinoscopy is an older method but continues to be an important tool in quantitative assessment and is necessary in particular situations. Retinoscopy can be done by using a reflecting mirror or by a self-illuminated retinoscope. The commonly used are the Lister's plane mirror or a streak retinoscope. The concave mirror is used when there is a media haze and you need a stronger illumination. The quantitative assessment of refractive error with autorefractometer is easy and quick, and with retinoscopy it requires more time and skill. Both the procedures have their value and place. Retinoscopy is useful in children and uncooperative patients. It is more accurate for assessment of a spherical error. It is cheap, gives additional information regarding media, and cycloplegia is often required. It has an additional advantage that it is free from machine-related errors. Autorefractometer, on the other hand, is useful in cooperative patients and repeat testing. It is more accurate for assessment of cylindrical error and its axis. It is expensive and more sophisticated, does not give additional information regarding media, and cycloplegia is usually not required. The history of retinoscopy goes back to 1859 when Sir William Bowman observed an interesting shadow while using an ophthalmoscope. And that of autorefractometer goes back to 1619 when Scheiner observed that the plane where the eye gets focused can be identified using two pinholes. Now both these observations, they tell us the importance of an accurate observation and analysis during all the clinical procedures that we do. Let us quickly see the procedure to measure the refractive error with autorefractometer. We can see it in this picture here, figure 2. The patient sits in front of the machine, the height is adjusted and the face is aligned with the help of chin rest and forehead band here. The patient looks at the target inside the machine. The observer focuses by the fine movements using the jockey here. The machine analyzes the rays reflected from the patient's eye and automatically gives the refractive error measurements. Each eye is assessed separately. The measurements can be seen on the screen and a printout can be taken, which is used for prescription of glasses. The process is quick, takes just a few seconds per eye. While with the autorefractometer, most of the task is done by the machine automatically. The retinoscopy has to be done manually and it requires more skill. So we need to study the procedure and understand it. The purpose, we all know, is to get an objective measurement of the refractive status of the eye. And the principle is to make the rays emerging from the observed eye come to focus at the plane of the observer's eye. It is based on Foucault's principle, which says that the divergence of the rays reflected from an illuminated fundus depends upon the refractive status of the eye. The instruments required for retinoscopy are illustrated in figure 3a and 3b. We need a plane or a concave mirror, retinoscope, and a source of light, or a self-illuminated streak retinoscopy where additional source of light is not needed. We need a set of trial lenses. Use of trial frame is optional. Plane mirror is mostly used. Concave mirror is used only when higher intensity of light is required, as in hazy media. The streak retinoscope has a inbuilt source of illumination, so additional light is not required, and the sleeve here in the streak retinoscope allows us to get a plane mirror effect or to get a concave mirror effect. As already said, the plane mirror or the plane mirror effect is more commonly used. The reflecting mirror retinoscope has certain advantages over the self-illuminated streak retinoscope in that it is cheaper and both axes can be observed simultaneously and compared easily. In a streak retinoscope, the direction of the streak has to be adjusted and one direction can be observed at one time. It has the disadvantages that it requires a separate light source. The glare may be annoying to the patient. Sometimes the reflexes may be confusing, and it is not possible to change the intensity or size of the beam, and at times it may be more difficult to identify the axis of cylinder. Both the instruments, the reflecting mirror retinoscope as well as the self-illuminated streak retinoscope, are in use for assessment of refractive errors. Continuing with the method of retinoscopy, the patient with or without cycloplegia sits in the dark room. The observer sits in front of the patient about an arm's length distance. The source of light is placed behind and to the side of the patient. And the observer reflects the light received from this source on his mirror onto the patient's eye and observes the red glow that is formed by the light rays reflected from the patient's retina. The procedure with the self-illuminated streak retinoscope is the same, except that the external source is not required. It itself has a light source which throws the light on the patient's eye. Now the reflected light from the patient's retina is observed as a red glow, and the observer makes his interpretations on the basis of the characteristic of the light of the red glow. So he observes the brightness, he observes the width, and he observes the direction and speed of movement of the glow associated with tilting of the mirror horizontally, vertically, or in the required direction. Each eye is tested separately. So in retinoscopy, there are these three stages almost happening simultaneously. There is the illumination stage where the light is directed onto the patient's eye, and there is the reflex stage when the image of the illuminated retina is formed at the patient's pupil, and there is the projection stage where the location of the image at the far point is assessed by observing the characteristics of this glow at the patient's pupillary plane. The characteristics of the glow at the pupil that we observe is the brightness, its width, its speed. And these characteristics, that means if it is dull, if it is narrow, or if the movement is slow, we are away from the neutralization point. That means we have a high refractive error. Whereas if it is bright, it is wide, and the movement is fast, we are closer to the neutralization point. It means that there is a low or no refractive error. The direction of the movement, whether it is with the movement of the mirror or if it is against the movement of the mirror, it tells us the type of refractive error and which lenses we would require. So if it is with the movement, we require plus lenses to neutralize this movement, and if it is against the movement, we require minus lenses to neutralize the movement. The illumination or the reflex at the pupillary plane is the widest and brightest at neutralization. That means that the rays from the patient's eye are converging at the plane of the retinoscopic mirror. As you move away from this neutralization point, towards the higher refractive errors, the illumination becomes duller and the width becomes thinner. In addition to the brightness and direction, the speed of movement gives us a rough idea as to how far away we are from the neutralization point. This is shown here. This is the speed. This is the how far away we are from the neutralization point. This is pictorially showing the speed of the movement. When far from neutralization, the reflex is dull and slow. When approaching near neutralization, the reflex becomes brighter and faster till at neutralization it is bright, occupies the whole pupil, and no movement is seen. The direction of movement depends upon the vergence of the rays reflected from the patient's illuminated fundus. If they focus at the plane of the mirror, then there is no movement. If they do not converge before reaching the mirror but would go behind if allowed to go, so that means they have not focused in between, then the movement is in the same direction as that of the mirror, and this happens in emetropia, hypermetropia, and myopia of less than 1 diopter distance. The movement is against if the rays converge before reaching the plane of the mirror, and this happens in myopia of more than 1 diopters. The interpretation of findings with the concave mirror is reverse of that with the plane mirror. This is because the direction of movement of the image of the bulb, which is the immediate source of light for the patient's eye, is opposite of that with the plane mirror. The movement of the red glow is neutralized by placing appropriate glasses in front of the patient's eye. If there is no movement to start with, it means that you need that is zero lens to neutralize. The neutralization is done at two identified axis and the reading is noted. Achieving no movement is the endpoint, and this can be confirmed by overcorrecting by 0.25 or zero point 0.5 lengths. It should cause a reversal of the movement. Moving slightly forward or backward, the former should cause with and the latter should cause against movement. At neutralization, the rays emerging from the patient's eye are converging at the plane of observer's mirror. That is, that the interposed lens has made the patient's eye myopic by the dioptric value for this distance. If the retinoscopic working distance is 50 centimeters, add -2 diopters, and if it is 1 meter, add -1 diopters to the interposed lens power. Additional -0.5 to -1 diopters has to be added to account for the ciliary tone. These are some examples of the retinoscopic findings and the calculated number that we would arrive at. So the retinoscopy is done at 1 meter distance. So these are the findings in the vertical meridian and in the horizontal meridian. Here we have the oblique axes, and the power would be by adding -1 for distance and -0.5 for the ciliary tone. So here we have 0 power for horizontal axis and 0 power for vertical axis, and we have a emetropia. Here we have 0 power for this axis and +1 diopter power for the vertical axis. So the power is 0 sphere and +1 diopter cylinder at 180 degrees. So this is simple hypermetropic astigmatism. Similarly, here we have at 15-degree axis 0 power, -3, -1.5, add -1.5, -3 diopter, and at this axis, which is about 105 degrees, plus 0.5, add -1.5, that is -1 diopter. So we have a power of -1 sphere and -2 cylinder at 15 degrees. This is compound myopic astigmatism. And here we have both the axes -1.5, so we have -3 diopter power in both the axes, and the power is -3 diopter sphere. This is myopia. The use of trial frame while doing retinoscopy is optional, and it is a personal choice. By adding a working distance allowance lens in the trial frame, there are certain advantages: that it gives an instant clue to myopia or hypermetropia, it may help in relaxing accommodation, and there is no need for further additions to the reading. The disadvantage is that extra reflections may be disturbing. Most of us do not use the working distance allowance lens in the trial frame while doing retinoscopy. We have discussed the basics and the procedure of retinoscopy. There may be some slight variations in how we do the retinoscopy depending upon where we ask the patient to focus. It may be static, dynamic, or just for near. It may be wet or dry. Wet is with cycloplegia and dry is without cycloplegia. And radical is done very rarely in patients who have non-dilating pupils. This is done from 20 centimeters distance. But most commonly what we do is retinoscopy at 1 meter distance, usually with cycloplegia in younger patients and without cycloplegia in older and cooperative patients. Let us now revise and also test our understanding of the procedures described here with the help of MCQs.